Welcome all again to the second half of day 2 sessions. In this part, we have with us Dr. Roshni Maiti from Department of Electrical Engineering, IIEST Shibpur, West Bengal. I take the opportunity to introduce Dr. Roshni Maiti before the participants. Dr. Maiti received her BTech degree in Electrical Engineering from West Bengal University of Technology, Kolkata in 2012. MTech degree in Electrical Engineering from University of Calcutta in 2014 and the PhD degree in Electrical Engineering with specialization control system from University of Kolkata in 2021. She served as a faculty member of MNNIT Allahabad in 2022. Presently, she is associated with the Electrical Engineering Department, IIEST Shibpur. Prior to her joining to IIEST Shibpur, she was associated as a postdoctoral fellow at IIT Kanpur in 2023. Her research area interest includes adaptive control designs, optimizations, intelligent controls, applications to robotics, and many more. So with these brief introductions, let me hand over the sessions to Dr. Maiti. Dr. Maiti, please proceed.
Thank you, sir, for your kind information. Now, let me share my screen. Sir, is my screen visible?
Yes, madam, it is visible.
Okay. So in the first half of this lecture, we have studied about the model-based architectures of different controllers or observers. Here, we will learn about the model-free observer or model-free controllers. At first, we have to know when we are concerned about any practical systems. Practical system consists of disturbances, uncertainties whose values are not known to us. Therefore, we can't model that one from the very beginning. For this one, we have to go for the model-free approach, where during the run process, online all those things, disturbances or uncertainties, we have to estimate. And after that, we have to reject those disturbances to make our overall system robust. Otherwise, if we do not have any prior information of those uncertainties and disturbances, and if we are going only with the nominal model, then any kind of disturbance will make our system unstable. Now, for any practical system, if it will become unstable, then it will cost huge. Its damage will be huge. Therefore, we have to think for some model-free approach where during iteration, we have to estimate those time-varying disturbances and uncertainties, and at the same time, we have to reject those things. For this one, we can do this one by using fuzzy-based controller or neural network-based controllers, etc. First, I will start with the fuzzy logic-based observer and its different controllers design. First, here we can see for the, here we have the classical set, or which is known as the crisp set, and another one is the fuzzy set. So for this one, whenever we have this crisp set, there it mainly depends upon the model. The exact model value we have to give to this. That means, let here one example is given where c is equals to x, where x will be greater than 6. So it's perfectly defined when that x will be a set of c. Therefore, its model is defined here. But in many cases, this model we can't define in a very crisp manner. So for that one, what we have to do, a particular value, it may stay with some percentage to different membership functions. So we at first have to define different membership functions. That means if there is some disturbance, the level of the disturbance may be very low, medium, very high. So in this way, at first, those membership function we have to define in 3 ways. One will be small, medium, another one will be large. After this, one value we have to put, and that disturbance we have to say this disturbance is x% belongs to the large and y% belongs to the medium. That means here one gradual boundary will be there. So if that disturbance will vary, then also we can exactly estimate that one and exactly eliminate that thing. So if I will goes on increasing, and I will give those examples, then this thing will be much more clearer to us. So first, here we have to know, for we have some crisp inputs. That means a specific inputs we have, and for this one also we have to provide some crisp output. But in between, we have to do the fuzzification of those crisp inputs. Then we have to formulate the rule base to generate the output. And after getting those output, we have to defuzzify those to again get some crisp outputs. So what does this mean? Before explaining that, we can have different types of fuzzy rules. Depending upon that, we can classify our fuzzy structures in main 2 modules. One is the Mamdani type inferencing and another one is the Sugenu type inferencing. So in case of Mamdani type, here we can see we will have some rule which will be very specific. That means here it is written, if x1 is a1, x2 is b1, then y will be c1. That means a specific output we will have if we have some specific inputs. In rule 2 again we have written x1 if a2, x2 b2, then again y will be c2. Rather, if we will compare this one with this Sugenu type inferencing, then we can see here if x1 is a1 and x2 is b1, then this f1, this will be a function of r1. That means this f1 will not be a specific constant value like c1. This will be a function which is dependent upon the inputs whatever we are giving. Therefore, from this too we can say, as this Sugenu model is dependent upon some function rather than a constant value, therefore any system can be represented more precisely by using this Sugenu type inferencing more than that of the Mamdani type inferencing. And these are the diff after fuzzification. Obviously, we have to do the defuzzification, and to do that defuzzification for Mamdani, we have different methods, and for Sugenu, we use generally the weighted average methods. Now, how this rule we have to formulate, that we will see here by using one example. Here we are doing a fuzzy control of a water heater. So here we can see that we have this water inlet and here water outlet, and we have this level sensor and a temperature sensor. And depending upon this level and the temperature, here our objective is to design a heat. We have to change the heat knob depending upon the level and the temperature of this system. Now here we can see the level of a system cannot be same, because here some perturbations will be there, which is known as the uncertainties, as well as if we will give some temperature will be very high, then some bubble will also be there. So these will be treated as some uncertainties and disturbances present into the system. Therefore, exact level we can't specify here, or the model of that exact level we can't design. Similarly, as this one is a practical system, so temperature will also not be constant. If we will make some temperature, let x degree, then after few time it will be x minus a degree, because some heat will radiate. Therefore, for practical system, we can't define that model very specifically. Therefore, what we have to do, we have to specify those in some membership functions, where first we have defined here the levels as this membership functions, where for this membership function we have to scale this one within 1. So here the ultimate, the maximum point will be 1. And for this one, the level sensors, so we have segregated them in X small, small, medium, large, and extra large. Similarly, here temperature sensor is also divided into some regions, and there again we have given them some name. Now we have given one input, that is 6. 6 will be our value of the level which we want to maintain, and here it is, the value is 68.25. This is the temperature which we want to maintain. Now for this one, here we can see at first this 6 value is not belongs to any one membership function. Rather, 6 is cutting this medium level at this point, which is at 0.4, and again this 6 is cutting the large level at this point, whose value is 0.6. Therefore, we can say that this crisp value 6 is belongs to 40% in medium membership function, and this 6 crisp value belongs to 60% in the large membership function. Similarly, for the temperature sensor, we have to maintain one temperature, that is 68.25. Now, if we will draw this line, then we can say this 68.25 belongs to 25% in large membership function, and it also belongs to 75% in medium membership function. Now, after getting this to value, we have to move to the third step. So here we are fuzzifying our inputs. After this, we have to generate another membership function for our output. Here our output will be the heat knob, where we have to fix our heat knob to maintain that level and that temperature. For heat knob, we again have defined some membership functions for this. And not only that, after this, we have created one if then rule base. Rule base, here we have designed this one for temperature sensors, and here we have the level sensors. They are different values, and for their combination, the heat knob we have to open this much, a good amount, a little amount for the combination of small for the temperature sensor and extra small for the level sensor. We have to open our heat knob a little. Then to maintain this one, medium and X small for temperature sensor and level sensor respectively, we have to open our heat knob very little. So these are different rules. After that, we have to specify those rules. After specifying this table, now we have to defuzzify our output. Now, how to get that decision? How to make this decision? So, here we can see 4 rules will be activated. First one will be temperature sensor. Temperature sensor will have its two values 0.75 and 0.25. If we will see in the previous slide, then we can see here this temperature sensor will have its two membership functions. One will be 0.25 and another one will be 0.75. And for this one, level sensors will have again two combinations. If again we will see in the previous slide, then we can see level sensors have its two combinations, that is 0.4 and 0.6. Now here, then we will have 4 combinations for temperature sensor, that is for medium 0.75. Here again we can see that this 6 is a cutting this with, here this one is a cutting the medium with 0.5 and it is cutting this large membership function with 0.25. So here we have written for this one medium 0.75, large 0.25. And here we have combined level sensor medium 0.4 and level sensor medium 0.4 with this two combination. Then we have medium 0.75 and large 0.25 of temperature sensor, and with that we have merged the level sensor of large 0.6, 0.6. So 4 combinations we are developing here. Now, after generating these 4 rules, here we have to see that for this one heat knob, that will be equals to, here we have to take the smallest between these two. So here the values are 0.75 and 0.4. So 0.75 and 0.4 we have taken, and the smallest between these two 0.4 we have taken. Now for this one, after this, again we have to check the combination of these two, and the smallest between these two we have to take. And From this combination, we have to see that here we have temperature sensor medium, level sensor medium. So temperature sensor medium and level sensor medium. For this one, we have a good amount. So heat knob will open a good amount with firing strength smaller between these two, that is with 0.4. The next one, temperature sensor is large and the level sensor is medium. So temperature sensor is large and level sensor is medium. Here it will be very little. So heat knob will open very little with firing strength smaller between these two, that is 0.25. In this way, we have to generate the if-then rules depending upon the current status of our input. So here we don't have any mathematical model of that level sensor and temperature sensor, and based upon that we are not giving that U, that is the control input, that is our heat knob. So here depending upon model we are not doing. We are doing dependent upon the data. So these are actually data driven control and not the model based control. Therefore, we are concerned about the current data, where our input data is now, and depending upon what our output will be, that we have to check. Now, for after this, we have now defusified our outputs, but till now, what will be our ultimate output? That till now we haven't opted. So this table again I am copying in the next slide, where we have obtained our decision, and that decision will be reflected on this membership function of this heat knob. So this curve and this table I am copying in the next slide. So here you can see that decision whatever we have taken, and this one is the membership function of that heat knob. Now depending upon that we have to determine the crisp output. So how to get that crisp output? Different types of defusification we can apply here. Here we have done the center of gravity defusification. For that one, how we have drawn this curve? First here we can see, here it will be a good amount with firing strength 0.4. So our good amount is here with this blue line. So this blue peak will be here with firing strength 0.4. So this is near about 0.4 or 40% of its total value. Next we will have very little with firing angle 0.25. So very little is here with its 0.25 amount. After this, a lot with a lot. So a lot is with this violet line. A lot will be with 0.6, means 60% of its value. It will have its 60% value. Next, we will have a little with firing strength 0.25. So a little is here with red lines. So here we have put it this one for the red lines with 0.25, means 25% value. After this, we have combined all of this four figures at here, and we have taken the resultant. We have calculated the center of gravity, and from that center of gravity, our output we have obtained as 4.82. So for the specific inputs where we need our level sensors at 6 and the temperature sensor at 68.25, there we have to open our heat knob 4.82. So in this way, depending upon the data, not on the model, we have to take the decisions. And During iterations, this is the iteration number 1. Now in iteration 2, if some disturbance or noise will be included, then as we are concerned about the data, not the model, therefore on that data, those disturbance and uncertainties will also be included. Therefore, if we will design one fuzzy logic to estimate those disturbances in terms of a disturbance observer, fuzzy model based disturbance observer, then from data we can exactly collect what is the disturbance present in my system, and from that we can eliminate those disturbances properly and we can control our system. So the previous one was the Mamdani model. Next one is the Sugenu model. In case of Sugenu model, the if-then rules dependent upon some function, not a specific value. So here we can see that in case of Sugenu model, where this one is the first order Sugenu model, in case of first order Sugenu model, here if we will have x is a1, y is b1, then our output will be some function of these inputs. X and y are our two inputs. So here we can see our output, which is f1, it is the function of x and y with some term, another term r1. This r1 may be disturbance or maybe some constant, anything we can include here. And in rule 2, we have given if x is a2, y is b2, then we will have the rule like this. So for only two rules, we have the output is equals to average weighted sum. Therefore, we have to multiply sum of weight to our function. W1 is the weight multiplied with the first function f1, and W2 is the second weight multiplied with the second function f2 divided by W1 by W2. Weighted average sum of this. So ultimately we have obtained this one, where W1 bar is the W1 by W1 plus W2 and W2 bar is the W2 by W1 plus W2. So such kind of n number of rules, we have to represent this one by using summation sign. So we can write summation over I equals to 1 to n wn fn divided by whole summation of the all w's. So in this way, for n number of rules, we can represent our system. So our system, we have defined our system in different zones. And if on those zones some disturbance or uncertainties will come, then we can estimate them very properly. So here we know that if we were concerned about the control system, we have to reject those disturbances to make our system stable. So with such kind of controllers, we have to show that our system is stable. Now to define this stability, if we have a non-linear system, here we have considered non-linear system because practical systems are generally of non-linear in nature. Therefore, we have to consider the non-linearities present in different systems. So here we have defined this state x dot is equals to f of x plus b into u, where this x are our state, this u is the input, and y is our output. Now, here we can take our reference model as this. This one is the xm. So, we will have some system output. Our aim is to track that output. And to track that output, we have to design the system in different zones. So ultimately our aim is to track the reference model. So to track the reference model, we have to generate whatever error is coming between this actual model and this mathematical model or reference model. So for this one, we have generated the tracking error. E is equals to y minus ym, where y is the actual output and ym is the output of that model. Nominal model we have considered here. Now, for this stability, we have to develop one controller such that our system states will be bounded. Here, we are not concerned about only the system states as well as whatever uncertainties or disturbances will be included in my system, that also should be bounded. So for this one, here we have to design one controller, and for this one, the ideal control law will be something like this. This ideal control law, if we will calculate this one from this function, if we will put their values in this reference model, then ultimately we will have the ideal control law as this. But as we know that the exact model is unknown to me, because we are dealing with some practical systems, some hardwares, and we are not doing this thing in simulation only. In simulation, we have the exact values of my model on which I can simulate. But for practical system, the exact model I don't have in my hand. Therefore, this f of x, b, all those values are not known to me precisely. Therefore, this ideal control law we can't generate. For this one, we can move to the fuzzy logic based control system. In case of fuzzy logic based control system, when we will develop the control signal, then this UC that will be given as theta into zeta, where this theta are the singleton values with which we are multiplying this zeta, where this zeta is the firing strength of that fuzzy rules, which we have already seen here for only two values. Here only for two rules we have shown this one, but to develop its stability analysis, we have to do this one in general, as a general case, means n number of rules we have to give there. For this one, here we can see if we have that capital N number of rules, then average weighted sum again we are doing. The same thing whatever we have done previously for the two values only, two rules only, here we are doing that one for n number of rules to generate this fuzzy logic control system. So here we will have this theta into zeta, and this alpha will have the membership function of those inputs. This alpha is the membership function, whatever percentage of membership of that input I have in different regions, that we have to put in this alpha. After this, here we can see, and this zeta value is equals to this alpha divided by summation of this total alpha. So this is the total ultimate fuzzy logic controller theta into zeta. Now, we don't want fuzzy logic controller. We want to develop a fuzzy logic observer. Then also the system model will be the observer value, let f cap x. That f cap x will be equals to theta into zeta. So these are the values depending upon the membership functions, we are developing any kind of model. It may be the model of the original system. It may be the model of the observer. It may be the model of the controller. Any kind of model now we can develop by using this fuzzy logic, where we have the ultimate value as this theta into zeta. Now, here we are doing this one for the controller. So, after this, we have generated the error for n number of states, and here ym of ym y of n, and if we ultimately calculate, then we will have the error vector like this, where a and b are given by this. Now, after developing up to this error vector, we have to calculate if this error will be bounded or not. That we have to check. Therefore, to check the boundedness or the stability of any nonlinear system, we have to go for Lyapunov stability analysis and Barbalat's lemma. So, for any here we are concerned about the nonlinear system. So here we are developing this Lyapunov candidate function, and here the Lyapunov candidate function we have chosen as this. And here we have put it we have taken its derivative we have calculated, and we have put it its value from here, where this E dot we have this value, and here we have put it the value of E dot. And ultimately we have seen that if this two term, this term and this term, if we can make them equal and we can find out some condition from that, then we will left with only this term. So VE dot should be less than equals to minus half E transpose QE. Only this term we need here. Therefore, this two term we have to make equals to 0, and from that we have to calculate whatever will be the condition of this controller. And ultimately we will have this VE dot is less than equals to minus half E transpose QE. And as this Q is a positive definite matrix, therefore we can comment this V dot will be a negative definite matrix. V dot means the rate of change of energy. Previously, Dipan sir has already told that this Lyapunov function means it is an energy function. So we need that the energy of the overall system should be lesser as the time will goes on. So that derivative of this energy function should be negative. That means the energy is goes on decreasing. So this is the derivative of that energy function, and here we have proved VE dot is less than equal to one positive definite matrix. That means VE dot is a negative definite matrix. And if this one will be a negative definite matrix, that means the energy function is rate of change of energy is reduced. Rate of change of energy is negative. That means energy is reducing, and if that energy will reduce, then our system will become stable. So not only that, after doing this Lyapunov stability analysis, we have came to the conclusion VE dot will be less than equals to minus this. So we can take this one as a Barbalat's lemma operator. This is known as the Barbalat's lemma operator, which is equals to this E transpose QE, this term only, which is less than equals to this minus V dot. Now, If we will take the integration of this term, then we will have this V0 minus V of t. This V dot we can represent by using this. Here we can see that V0 and Vt both are bounded, and here we can see that V0 and Vt, as we have seen, these are less than equals to this. So we can say that this both are bounded, and also we can see that the last term is non-increasing, because this Vt is a decreasing term, because our error is decreasing. So this one is also non-increasing. Therefore, if we will take the integration of this term, then it should be with less than infinite, and this Barbalat's lemma operator, this psi dot t, will be bounded. And from this one, we can say from the Barbalat's lemma that limit t tends to infinity, psi t is equals to 0, which again implies in turns that limit t tends to infinity, mod of et will be equals to 0, which indicates that our error will goes on 0 as t tends to infinity. That means our system state will goes on, system state will go to the state of our reference system model. So system output will go to the reference system model, and overall our system will become stable. So up to this, we have discussed about the fuzzy logic controller. And in a similar way, by using this fuzzy logic, so we can design the fuzzy observer as well. And in the tutorial, I will discuss that fuzzy observer also. So next we will see few more things about the neural networks. Before that, if anyone have any question from this, then they can ask.
Are there any query from the participant sides? Ma'am, you can continue, please.
Okay. Then we can continue to the next one, that is the another type of model-free control we are now discussing, and this one we will implement on a robot manipulator. So first, here some problem statements and some definitions are given, that is the modeling and identification of nonlinear dynamics, because we all know this robot manipulator is obviously a nonlinear system. After this, this robust controller design, we have to design the robust controller for trajectory we have to design the robust controller for any kind of practical system. So different kinds of controller we can design here, different sliding mode controllers or adaptive controllers, as well as this fuzzy controller or neural network based controller. Different types of controllers so we can design there. Not only that, we can design this sliding controller or PID controller by using fuzzy controller or neural network. That also we can do. So for ultimate, our main ultimate objective is to design the trajectory tracking, and then we have to go for the stability analysis. These are some another things given here: parametric uncertainties and the external disturbances which we have to eliminate. So for this one, first we have to, if we have the mathematical model of that robot manipulator, that can be represented by this, where this M is the symmetric inertia matrix, and this C is the centrifugal Coriolis matrix, G is the gravitational matrix, and this tau D is the disturbance what we want to estimate, and this tau is the input which we have to give. So if this one will be a two-link robot manipulator, then two inputs we have to give, and state, this Q are the state vectors. These are state vectors. We will have 4 state vectors for 2 for each of the links. So for this one, we can have the again we can have this system model, and from this one we can design the Lyapunov stability similar to the previous one. Here, similar to the previous one, again we have designed the P matrix, that is our Lyapunov matrix, and we have taken its V dot, and ultimately we have to show that V dot, that is the energy, rate of change of energy is goes on decreasing. That we have to show ultimately by using the Lyapunov stability criteria. Here again we have shown that one by using that. Here again we can do the model-free controller design or model-free system design or observer design by using different types of neural networks. Here at first we have designed this one by using this RBF, where we have only one hidden layers and the activation function. So we have defined here, and our aim is to obtain the ultimate output from this, and for this one we have to change those weights, and here we can see that RBF NN output, this will be the function of the weighted sum of this activation function. Overall, we can write this function as this. Now, here we can design this one by using adaptive rules as well. So for fuzzy also, we can design that theta, whatever value we are multiplying with that weight, that we can design by using those adaptive rules, and those adaptive rules will also be formulated from the Lyapunov stability criteria. So different weights, so we can design here, and for such kind of neural network, here we have given this one. If my observer model will be like this, which is also developed by using this neural network, and then we can design our control law as this. We will have our control law ultimately by using this formula, where this tau is the sliding mode controller. Here we have augmented sliding mode controller with this. So a simple sliding mode controller with this value we have given here. Sliding surface we have chosen as this, and this is the error vector, state error vector, where QD is the desired state, and this Q is our output state, whatever we are getting. And for this one, the adaptive rules, so which we have formulated from the Lyapunov stability criteria, that will be given by this, where this 3 terms, so we can different terms, so we can adapt depending upon the Lyapunov function. We have to choose the Lyapunov function as a way that we can get different adaptive functions whose value we want to adapt. We have to give those things inside our Lyapunov function, and from that stability condition we have to derive their adaptive rules. So ultimately here we can see in this Lyapunov function we have given these values W, C and D. So we have given W, C and D. So whose value we want to adapt, those value we have to give inside our Lyapunov function, and from this stability criteria we have to develop its adaptive rule as a way that those adaptive rules should be bounded, and it will ultimately give me a stabilized control system. Therefore, we have to put those things inside our Lyapunov vector. And ultimately, if we will calculate these things again, then we will have different values like this, and ultimately we will have our rate of change of energy, that is V dot, as a negative semi-definite function. So in this way, we have designed different model-free controller as well as observer or system we can have, and these are we are designing by using different data available with us. So these are known as the basically data-driven control rather than the model-based control. So whenever we are concerned about to control any practical system, then we have to go for such kind of data-driven intelligent control systems. So here I am ending this talk. Thank you. So again, if you have any question from this, then you can ask me. Hello, sir. I have completed. So if anyone have any question or
Yes, madam. Thank you. So, participants, any other queries? Okay, ma'am, we can proceed for the tutorial sessions.
okay, sir.
Participants, there are two, in the tutorial session, we will solve two problems. Uh, we will try to show you the numerical simulations. Uh, so one phase will be covered by Dr. Maiti, and the second phase I will discuss or shared with all of you. So, Dr. Maiti, you please proceed with your sessions.
Yes. Okay. So for the tutorial, here we have two systems with us. One is the one robot manipulator, another one I will show as a twin rotor MIMO system. So here we can see that we have this robot manipulator, which is a two-link robot manipulator, and here it has its two links. This one is its first link, and this one is the second link. And here we have two servo motors, so which are uh, driving this system. So as a whole, whenever we want to model this system, we can have different uncertainties, unmodeled dynamics, and disturbances present into the system. Therefore, here we have modeled this system. So this is the nominal model of the system where we have used this data. Now, if different uncertainties or disturbances will come into the system, then we have different kinds of data driven disturbance observer or controller to eliminate those things. Here at first we have designed this RBFNN. Those its different values are given here, And for that one, we have the results for this one, where we can see that the values of this, its tracking values are given here, where this blue line is the desired actual one, and this red line is the desired one, which is given over here. And for this one, the control input also we have to show here. Therefore, we can see that the control input is also within the boundary for two motors. One is the tau 1 and another one is the tau 2. One is for first motor and another, this input is for second motor. So both of these two motors we have two inputs, and these are the errors. Whatever error we have during the tracking, that is also shown here. And these are the velocity tracking error. So velocity tracking error is also provided here. So if we can zoom this one, then we can see their disturbance is more in case of velocity error, because here we are taking the differentiation of this position error. So here the disturbance will move in case of velocity tracking error. So therefore, in practical system on those servo motors, position encoders are there to reduce the noise, external noise, to reduce those noise from the manufacturers. Already their position sensors are there in those servo motors, that the noise can be eliminated at first, because in velocity sensor the noise will be much higher, but still there are very much noises present in the system, and for that one we have to develop those observers and different types of controllers. These are the control inputs for the first link and second link. So next one, we have designed one fuzzy observer. For this fuzzy observer based sliding mode controller for one twin rotor MIMO system. Here, this is a model of a twin rotor MIMO system where we have these two rotors. This one is the pitch rotor and this one is the yaw rotor, and our main aim is to control those two things by eliminating whatever disturbances are present in the system. For this one, we have designed here fuzzy observer based sliding mode controller for this twin rotor MIMO system. For twin rotor MIMO system, here also we can see we have two motors. One is for this pitch rotor and another one is for this yaw rotor. For this movement of this pitch rotor, one motor, that black one is the motor attached to this, and this one is the yaw rotor. Here again one motor is attached to this, and there also position encoders are there, and from that one we are getting the output from this system. Now for this one, here we have plotted two outputs of this system, and this blue one is the desired and this red one is the output whatever we are getting for the pitch, and this result, the second result, this result is for the yaw. So for pitch and for yaw, we have given their outputs, whatever output we are getting with respect to the desired, whatever desired reference we have to track. For this one, the control signal requires is given here. This control signal, so we have to give it to our twin rotor MIMO system to track this trajectory. And for this one, here the disturbance, whatever disturbance we have given to our system, here we can see that for these are the disturbances in pitch rotor and this is the disturbance in yaw rotor. So here we can see whatever disturbance we have given, it can track those disturbances very properly. And if can track those disturbances, that means our fuzzy disturbance observer has estimated those disturbance in a very proper manner for each iteration, and therefore we can reject those disturbances also very properly. And for both the pitch rotor and the ear rotor, we can see we can reject those disturbances very well. Now, these are the results which we have obtained from such kind of fuzzy logic controllers and all. So how to do their programming? To solve those systems, what our main motivation is, if we have the nominal system model, then we can use that system model. Otherwise, we have to go for fuzzy system modeling. Or what we can do, we can have that model of that system. From the output of the practical system, we can have the overall system model as well as the uncertainties and external disturbances present on that system. So after obtaining that model, we have to solve that system model, because we know all these system models are differential equations. So we have to solve those differential equations by using any kind of numerical methods. It may be Euler methods or it may be RK methods, different types of numerical methods so we can use to solve those system models to obtain its output value. Because here if we will see that these models are given by this, here we have the model, that is state vector, state q, then q dot, q double dot. So these are differential equations. So to solve, we have to solve that differential equation, and we have to find out the value of q, which is our state, and that y will be equals to c into x. From that one we can get our output. So ultimately we have to solve that system. After solving that system, we have our output in our hand. After obtaining that output contains external disturbances, uncertainties, all those things, unmodeled dynamics, so all those things are included in my system, in my output. Therefore, that output is at first given to a fuzzy disturbance observer, where we have to design this fuzzy disturbance observer by using the fuzzy logic. And I have shown you, for that fuzzy logic we have to build different rules. N number of rules we have to formulate for each of the inputs. X1 will be equals to A1, X2 will be equals to B2. In this way, how many states we have, for all those states we have to take as the input of the fuzzy logic model. After that, we have to calculate the output y. That output y will be the average weighted sum or weighted average sum. So we will get y is equals to theta into zeta ultimately. So that theta into zeta will be the estimate of that disturbance which is present in my system. So in each iteration, this block will give me the estimate of this theta into zeta depending upon the value of x1, x2 and so on. Here for the twin rotor MIMO system, we will have 6 states. Therefore, from x1 to x6, we will have different values a1, b1, c1 like this, and such kind of different rules also we have to formulate for fuzzy, and ultimately we have to calculate the membership value, percentage of membership value of each input which may stay on that region. And from that one, we have to calculate the ultimate disturbance value theta into zeta. After getting the theta zeta value, we have to give that one again to our system model, that it can be eliminated from that, because in my system model those uncertainties and disturbances are present. So after estimating those things, I have to nullify that one from my system model. Now, after nullifying those disturbances and uncertainties, I have my nominal system model in my hand. After this, that system has to track one reference. Therefore, I have to attach one controller that will give some control input to this system, that this system can track, system output can track the reference input or reference model, reference value properly. This is our main motivation. So for this one, if I will show you this, so ultimately here we have designed this control system. We have iterated this one. Here we have designed this plant and this predictor or this observer model, and this one we have done by using this fuzzy observer. In this fuzzy observer, we have given two inputs. Two input we have, this one are our two inputs we have given as the input of this fuzzy observer, and ultimately here this one, if we will see, this one is a twin rotor MIMO system. Here we will have 6 states, as I have already told, 6 states. So in initialization we can see 6 values we have given for initialization. And here I have told you that we have 2 control inputs. Here U is our control inputs. So 2 control inputs we have initialized, and we will these 2 control inputs are for the 2 DC motors of pitch rotor and yaw rotor, and ultimately we will get 2 outputs from this. Output is represented with this Y. So ultimately we will have 2 position values. One is from pitch rotor and another is from yaw rotor. So for both of these two, we will have 2 output values as well. So after this one, we have to calculate the membership functions for input 1 and then membership function for input 2. Then we have to formulate that rule base, and then we have to calculate this zeta. And we have to multiply this zeta with this theta. Here theta is written as gamma because other theta is there in this system. So ultimately here we are calculating this theta. So ultimately we are getting total theta into zeta, which is our observed disturbance. So whatever disturbance we are observing, that we have estimated by using this fuzzy logic based observer. After this, I have shown you, after observer also we need that controller, and here I have used the sliding mode control. So for this one, I have designed one sliding mode control for each, another sliding mode control surface I have taken for yaw, and ultimately I have designed the sliding mode controller for this. And this one, this overall system is my plant model. So this one is my plant model, which I have solved by using RK method. And this one is my observer model, which again I have solved by using the RK method. And ultimately I am getting my output here, which I have plot here. So if I will run this system, so here we can see that whatever disturbance we have given, it is tracking them very properly. These are the disturbance. Whatever we have given for pitch, it is tracking this one properly. Here the disturbance is for EO. It is also tracking this one very properly. And these results are for fuzzy disturbance observer. By using this fuzzy disturbance observer, we can estimate those disturbance very properly, and if we can eliminate those disturbances, then this one is my tracking. Tracking for this one is the tracking of the pitch rotor, and this one is the tracking of the ear rotor. So it is tracking those very properly, and this is my control input. Whatever control input we require, that is given here. So this is the ultimate thing through which, by using this data driven thing, we have to proceed. So by using those datas, ultimately without model, we can generate our observers or controllers or whatever thing we need for our control system, and we can design their stability analysis. We have shown their stability analysis as well. Therefore, we can say that whatever things we have designed, they are also stable systems. So this is all for today's presentation. Thank you. Sir, I have completed this.
Yeah, thank you, madam. Thank you. We can take queries if the participants have.
Ma'am, what is the step size that you have used for RK method, ma'am?
For RK method, I have used 0.01 most probably. I can we can use 0.01 step size I have used, and the total simulation time I have used as 100.
Is there any other queries? Okay, thank you, ma'am. Is my voice audible?
Yes, sir. Yes.
Thank you, ma'am, once again for your such an informative sessions, and you have also detailed the process of designing this type of model-free observers based control algorithms in the simulation platforms, and you have shown the stability analysis using the Lyapunov and Barbalat lemma rigorously for a nonlinear control system problem. And I believe that the participants have gained considerable inputs from your presentations, and hopefully they will also apply these ideas in their own problem, whether it is in a CPS framework or not in a CPS framework. So thank you once again. So now
Thank you,
we
sir.
are, yeah, thank you, ma'am.